Let's look at the last case of the damped harmonic oscillator, which is when there's two distinct real roots to the characteristic equation, and that gives us overdamping. So when are there two distinct real roots? We have gamma over 2m squared minus k over m is greater than 0, and so gamma is greater than 2 times the root of km. We solved this with an equal sign last time. I'm just replacing that with a greater than. So what does that mean? That's gamma is the damping constant is big compared to the spring constant and the mass. Okay, to make this a little bit nicer, I'm going to let mu equal the root of exactly what's inside this time, since we don't need an I. Similar thing we did with complex, except it was reversed. That time we had an I. So r is negative gamma over 2m plus or minus mu. So then we get the general solution. Remember, this was the easy case of solving. We had e to 1 root times t plus some constant times e to some other root times t. So first root is plus mu times t plus c2 e to the negative gamma over 2m minus mu times t. And then we're going to use exponent rules. So we'll write these separately. E to the negative gamma over 2m t e to the mu t. This is adding exponents, is multiplying in the base, e to the negative gamma over 2mt, and then e to the negative mu t. And now we can factor out this e to the negative gamma over 2mt, and we're left with c1 e to the mu t plus c2 e to the negative mu t. Okay, and we could leave it this way. That's fine. Or we can write this as, we're going to make up some new functions. We're not making it up specifically for this. These functions exist, but you may not have worked a lot with them before. They're called cosh and sinh. This is a similar trick to when we did complex roots. Changing these, remember when we had complex exponents, we changed them to cosine and sine to get the real part. This is similar. So, and also remember, so if you play around with Euler's formula, you can get these identities. Cosine of x is e to the ix, this is regular cosine, plus e to the negative ix over 2. And then sine of x is e to the ix minus e to the negative ix over 2. 2i. Okay. Then we can just analogously define cosh and sinh. Cosh is actually much nicer. It's just real exponents. E to the, you can do it with complex, but we can completely define it with real numbers. We don't need i's. And then sinh is e to the x minus e to the negative x over 2. Okay, nice properties. The derivative of cosh, you can actually calculate it, is going to be equal to sinh. And the derivative of sinh is going to be equal to cosh. So they're actually nicer than sine and cosine. You don't get negative signs. So these are actually solutions to the differential equation y double prime equals y. Whereas these guys are solutions to the differential equation y double prime equals negative y. So cool way that they come up in differential equations. Let's go back to, since you may not have had these definitions of sine and cosine until very recently, let's go back to your original definitions of sine and cosine, and we'll see why actually these are called sinh and cosh, and how they came up. So, hopefully, maybe not, but hopefully your original definition of sine and cosine was you took a circle, unit circle, which had the equation x squared plus y squared equals 1. You took an angle, theta, with the positive x-axis, measured in radians, and you called this point cosine theta, comma sine theta. That should be your definition of sine and cosine. If you didn't get this definition and you got one in terms of angle and triangles, you can see that this is equivalent, but this is the better way to define them. Okay, and really, these are misnamed. I think these should be called cosk and sinh. Y for circular circular sine and cosine. That's what these should be called. Because the other ones, cosh and sinh, stand for hyperbolic sine and cosine. Cosc and sinc are not a thing. But if you want, you can help me popularize them. You can start calling them that, and maybe the whole world will follow. Probably not. But there's a hope. So what happens? Here, this was x squared plus y squared equals 1. Now we're going to work with x squared minus y squared equals 1. I don't know how much experience you have in graphing hyperbolas. All of this is pre-calculus. So depending on the quality of your pre-calculus class and how long ago it was, you may or may not have ever learned this, or you may or may not remember this. So you get these hyperbolas. These are rectangular hyperbolas. This is not very good. These are supposed to be at 45-degree angles. Whatever. Your graph looks something like this, and then you do the exact same thing. You take an angle of theta, and now this is the point cosh theta, comma, sinh theta. Notice that theta can't be between pi over 4 and 3 pi over 4. But it is defined for lots of values, and you can do cool things with it. So that's how cosh and sinh are really related to cosine and sine.